Now in beta decay transformed neutrons and protons. This emissions of electrons or positrons from a nucleus is surprising or very strange. Why? We know before the nucleus is consists of protons and neutrons, and here the emission was electron and positron. This is look like very strange. Either a neutron is transformed into protons. Now here, look here, neutron transformed to protons, creating an electron in this process. And here, proton is transformed into neutron, creating positron in this process. Now, 2-beta decay can be written as this method. Now, decay events can be written in this method because other particles in the nucleus, like electron for example, much like the electrons around the nucleus, and don't directly participate in the beta decay. The electron and positron involved in beta decay, on other hand, are produced in the nuclear decay process because they don't come from the shells around the nucleus. This reason we can not be ignore it. Now we are going to explaining neutrinos and antineutrinos are emitted in beta decay. Before concluding our discussion of beta decay, there's one problem. It needs resolving. When the scientists analyzed the experimental results of beta decay reactions, they noticed disturbing fact. When the carbon 15 in beta decay actually occurred, as described in the previous page, energy and linear momentum and angular momentum would not be conserved. It's impossible. But in 1930, the scientist Pauli proposed that the third particle must be missing from the equation. There's a part is losing in the equation. He reasoned that this new particle called neutrino, this particle is called neutrino, is necessary to conserve energy and momentum. He solved the problem. Experimental evidence confirmed the existence of such particle in 1956. The Greek letter neutrino is used to represent a neutrino. When we put a bar in the drawing above the neutrino, it's called antineutrino or antiparticle of neutrino. Now, there are some properties of neutrino. Number one, the neutrino has zero electric charge, and the neutrino mass was once believed to be zero, but recent experiments suggest a very small non-zero mass, much smaller than the mass of electron, smaller the electron. Number three, the neutrino interacts very weakly with matter and is therefore very difficult to detect. Now, note the neutrino has no electric charge. The neutrino has no electric charge, and that mass is very small, perhaps even zero. As a result, a neutrino is difficult to detect experimentally. Now with the neutrino, we can describe the beta decay process of carbon 14 in form. Carbon produce nitrogen plus electron plus antineutrino. Now in beta decay we can say an electron is always accompanied by an antineutrino, and a positron is always accompanied by neutrino. Now high energy photons are emitted in gamma decay. When a nucleus that undergoes a radioactive decay, either alpha or beta is left in an excited energy state. Now the nucleus can then undergo a gamma decay in which one or more nucleons make transitions from higher energy level to a lower energy level. What happened in this process? One or more photons are emitted. like photons or gamma decay or gamma rays, have a very high energy relative to the energy of visible light. Now, the process of nuclear de-excitation or gamma decay is very similar to the emission of light by an atom. There's similarization between the visible light and gamma decay. Now, in which an electron makes a transition from state higher energy to state of lower energy. The energy is emitted, but the part of the nucleus are left unchanged. So, both of the atomic number and the mass number stay the same. No change in the nucleus. Now, gamma decay is still considered to be a form of nuclear decay. The reason it involves protons or neutrons in the nucleus. Now we have two reasons for a nucleus being in an excited state are alpha and beta. Here, if I ask you, what are the reasons for a nucleus being in an excited state, you have to answer alpha and beta decay. Now, if we follow the sequence of events that represent a typical situation in which gamma decay. Boron produce carbon. Now, the asterisk indicates that the carbon nucleus is left in an excited state following the decay. The excited carbon nucleus then decay in the second step to the ground state by emitting a gamma decay.